Let's minimize it so that it doesn't block yours. It wasn't.
I know.
Okay, this side. Does anybody know how to minimize? More?
Yes.
Oh, fantastic. Thank you. Okay, so
And you can minimize this.
I can minimize this.
The little line.
Thank you. It's been a while with this one. Okay, fantastic. So this is joint work with Laura Lopez and Sanjay Singh, who are sitting with us here in the room, and it's called a behavioral foundation for the investment wedge. Okay, so in this paper, we're going to address a classic problem in macroeconomics, which is that on the one hand, there is this idea that aggregate fluctuations in investment are an important driver of the business cycle. And indeed, historically, we have observed several instances, several episodes, where an investment boom is followed by an investment bust, episodes in which the stock market and real economic activity appear to be deeply interconnected. Now, however, when it comes to the modeling side of things, it turns out that capturing these ideas in dynamic general equilibrium models is actually not straightforward. So the challenge that typically arises is that it is hard to generate in standard frameworks the kind of co-movement that we observe in the data between real variables and financial variables. Now, this idea being important, as you might imagine, there's a large literature attempting to address it. So what is it that we're going to try to bring to the table here? What we want to do here is argue that a particular, thank you so much, Martin. So we want to argue that a particular behavioral friction, the one we are going to consider, is a useful step forward, a proactive step forward in addressing this problem. The friction is going to be given by a model of behavioral firms who systematically underestimate their competitors' investment. Because of that, firms in our model are going to, when good investment opportunities come around, they're going to overestimate the returns to the investment, and therefore they're going to end up overinvesting. So we're going to borrow this idea from a behavioral I/O paper by Greenwood and Hanson in the QJE 2015. Greenwood and Hanson call this friction competition neglect, a term that we're going to embrace and use throughout the paper. So, what could give rise to competition neglect? Greenwood and Hanson, in fact, discuss several heuristics and biases that can give rise to it. One that I like to tell is the Svensson better than average effect. So the fact that people typically like to think that they're better than others, than their peers, when it comes to tasks that involve some competence, especially. So applied to our firms, you might think that our firms in our model, when investment opportunities come around, they feel that they're somewhat special in their ability to identify those opportunities. Okay, so one story that we tell in the paper is from an interview to a person named Roth when he was chairman of Disney, where he was asked, "Hey, do you think it makes sense that every year we have so many big budget movies come out the same weekends?" And he says, "No, of course not. It doesn't make sense. It's a reflection of hubris. Hubris. You think you have a great idea. You think you have a great marketing department. You spend a lot in the movie. And then at the end of the day to realize, and this happens every year, that, there's always too many, other people have good ideas too. And so therefore, it just happens that every weekend, every year in the same weekend, the big budget movies come out and there's just not enough people to fill in the cinemas." Right? In our job, for example, you may be hearing something about that's going on in the real world. And one day you're walking down the park and you have a flash of inspiration and you say, "Wow, that's a really great idea. I need to write a paper on that." You call your friends, you spend a lot of time writing the paper, to realize when you go to these conferences that other people have good ideas too. And there's also other papers, perhaps not addressing the exact question you were addressing, but those papers are also not bad, and you end up facing sort of more competition than you had anticipated. So this is the idea of competition neglect, kind of, that we're going to apply to investment in a standard investment problem in this paper. There is the well-known handbook chapter by Angeletos and Lian discusses several theories of what could be given rise to this type of limited general equilibrium understanding by agents. In our paper, they discuss, for example, level K, lack of common knowledge. In the paper that we're going to present today, we're actually not going to have anything interesting to say about what exactly is giving rise to this type of behavior. Our job, the way we see it, is we're going to take the Greenwood-Hansen specification of the investment problem, which is actually a very nice one, and we want to do two things. Number one, we want to figure out how you do it in general equilibrium. The Greenwood-Hansen paper is in partial equilibrium, and so there are some technical things that one needs to deal with before getting a general equilibrium solution. And number two, we want to figure out what it brings to the table for macroeconomics. Here's where we are. Number one, we developed a solution method for general equilibrium models with competition neglect. The solution method is portable and can be applied to a wide range of dynamic stochastic general equilibrium models. Number two, when applied to RBC, competition neglect implies an endogenous investment wedge. This endogenous investment wedge has a time series representation that implies boom-bust investment dynamics. Number three, in RBC, competition neglect is going to generate the right co-movement between real and financial variables. And what's remarkable about this result is, like I said, this is a plain vanilla RBC specification. So this holds even in the absence of other frictions. And number four, this is going to be the sort of kind of ultimate point that differentiates our approach to other approaches to generate boom-bust cycles under rational expectations, is that we're going to quantitatively match firm earnings survey evidence coming from the Borrallo, Giamaioli, Laporta et al. Macro annual paper. And we're going to also show that the model does a good job at matching other financial moments, such as stock price volatility and return predictability. So the roadmap for the talk is the following. I'm going to start with a toy model that is going to illustrate, hopefully in an elegant way, what competition neglect brings to the table in an investment problem. And I'm going to do this taking the Muth 1961 classic commodity market model. After that, I'm going to turn to RBC with competition neglect. Then I'm going to turn to a fuller quantitative analysis. And then I'm going to give you what we think are the takeaways at this moment. All right, so this is Muth 1961, the classic econometrica, rational expectations and the theory of price movements. So this is a model of an isolated market for a commodity. Variables here are denoted in deviations from steady state. The demand side is modeled with a downward sloping function of the price, KB. There's a demand shifter that is stochastic and follows an AR1 process. The supply side is modeled with a time to build investment assumption. So the investment of firm IIT, is given by the expectation of the price of the commodity in the next period. And now this expectation operator is where competition neglect is going to enter. This is why there's a super index omega, which is the competition neglect parameter. So it's going to be the distorted expectation. I'm going to tell you in detail what that means in the next slide. Aggregate investment, IT, is given by the integral of investment across firms, and the supply side is given by a standard capital dynamics equation. Market clearing requires that the demand is equal to supply. All right, so what is the competition neglect assumption? The competition neglect assumption embodies the idea that firms underweight the responses of other firms. So each firm I perceives aggregate investment as, so the distorted expectation of aggregate investment is equal to omega times your own investment, where omega is between 0 and 1. Omega equals to 1 means rational expectations. Omega strictly smaller than 1 means competition neglect. So the firm is underweighting the responses of other firms. Omega is the competition neglect parameter. And so what this means basically is, suppose the shock is positive. So this means firms underestimate the reaction of aggregate investment, meaning firms underestimate the future amount of capital, and they overestimate the future price. And so that's going to push them to invest too much excessively compared to rational expectations. And so that's kind of like the key ingredient. This is going to be also the key reasoning that is going to go through in RBC. This is why we think this example this toy model is used. But it's basically a failure of the firms to understand the market equilibrium. So we can solve the model. It's very easy. So how do you do that?
We can interact. Yeah. Okay, getting back to, yeah. It's a little weird because suppose that, so.
If you have a question, could you speak into one of the microphones?
Can you pass?
Mike's.
The internet. Hello, internet people. No. So here it depends on also my belief about the rest of the world depends on my idiosyncratic shocks. So you have maybe other traditional models of neglect. It would be, I form a view of what other people are going to do, and then I dampen that. So it would be omega, for instance, rational expectation, omega less than 1 times rational expectation of future aggregate investment. Otherwise, it seems very, very dependent on my purely idiosyncratic shocks. It sounds like that won't generalize well.
So just to clarify, there's no idiosyncratic shocks here. Firms are identical.
Well, right, but either way, idiosyncratic shocks, that would not generalize correctly.
In a different way. So we want to, just notation-wise, we're trying to make an effort to stick to the Greenwood-Hanson notation. Yeah. But that's very interesting. Yeah. So okay, so to get a solution, you use market clearing, you invert the demand function, and you plug that into the individual investment. So this tells you investment today for I depends on its expectation of the future value of the demand shifter minus the capital stock. Okay, you substitute in the capital dynamics, you get the equation in the middle. And now is the moment where we use the competition neglect assumption. So basically, to compute that expectation, what's going to be distorted is the expectation of investment tomorrow, which is going to be equal to omega times IIT. Remember, omega is strictly smaller than 1 when there is competition neglect. So this is the piece that gets distorted. And kind of important just to make sure that we're on the same page, nothing else gets distorted. So the firm is able to compute the correct expectation of the future demand shifter. So has the correct expectation of the future value of the demand shifter. And also the assumption is that firms wake up, they observe the total capital stock, KT today, and they're therefore able to perfectly forecast the undepreciated fraction of it tomorrow, 1 minus delta KT. So the only place where there's a distortion is sort of in a cross-sectional way when the firm computes the expectation of aggregate investment. But just to clarify, firms are identical, there are no idiosyncratic shocks, okay?
Just one thing, if you did a cross-section of expectations, does this mean that firms underestimate what's going to happen to aggregate Y?
To aggregate Y, you mean aggregate capital?
Given that they're so they're thinking, I'm going to invest a lot, but nobody else is. I presume, but don't know for a fact, that must also mean that they underpredict Y. Which is a little questionable. I mean, it's worth thinking about because then you have firms investing in, when you ask them, hey, do you think it's a good time to invest from the perspective of macro? They're not particularly, but I have a really good idea. That's different than the old Schleifer thing where things are going to be hot, so I want to invest.
So here firms, so what matters, and this is going to go through in RBC too, as well, is what matters is the expectation firms have about the stream of returns going forward. Okay. And so in a recursive way, in the model is going to be recursive, so then expectation of the future return tomorrow. So the marginal productivity of capital. And that's where the place where my belief about how many people are distorted
Well, that I
today.
understand, but there's another, we shouldn't waste time on that, but it's
Okay,
worth thinking
maybe.
about. It's
So we
survey and other implications in a survey, it seems you have a particular prediction about the nature of errors.
which we do have predictions, and we're gonna, we're gonna do something on the forecast errors. I'm gonna show later, but okay. When you said why, you meant GDP, right?
I mean, aggregate GDP,
Yeah. Okay. So
not firm specific.
that's gonna be dealt with in the solution method. So here we don't have GDP. This is just like a partial equilibrium model. Let me discuss a little bit when we turn to RBC how we handle that. Okay, perfect. So this is the same equation that you had in the previous slide. And so I'm going to be using color notation to denote two different effects. In red, the competition neglect effect, and in orange, another effect that is going to come from a stock overhang accumulation and a correction that is going to imply. I'm denoting these two colors to kind of like, because I'm going to be using these colors in the future slides, and so just to flag. But before going there, so let me just say the solution is what you see there down there. That's the equilibrium level of investment, which is just solving for IIP there. And here, notice this minus sign embodies something that we like a lot and we want to emphasize, which is that this is a game of strategic substitutes. And that's kind of like where competition neglect is going to be kind of a good friction to introduce. Basically, this means the more other firms invest, the less your incentives to invest in this investment in this game, and competition neglect is disrupting that part there. Okay, so it's not making you realize that other firms are also investing, and that's moving the return of investment against you, and so you should not invest as much. So under competition neglect, you're going to invest more than under rational expectations, and this is going to be the source of a boom in investment at time t and onwards, because omega is strictly smaller than 1. Now, there's the other effect that is kind of fun, which is that there's going to be a bust at t plus 1 going forward, because firms are going to wake up, they're going to see, oh my God, there's too much capital in the economy, and so I need to cut my investment. And at some point, this effect is going to dominate and it's going to generate a bust. So there's some sort of thing that we'd like to call a tug of war between these two things. So to understand, and these are modulated by omega and delta. So let me explain how that works by shutting down our orange effect. So delta equals to 1. This is this proposition here, no storage benchmark. This is actually similar to a result in Angeletos and Lian in a consumption model. So here you have a boom where, the proposition says assume that delta is equal to 1. Furthermore, assume that at t minus 1, the economy is in steady state and epsilon is positive. Then the IRF of investment is such that it responds by more to the shock under competition neglect. And always forever. So competition neglect generates overinvestment with decaying dynamics at a rate delta. The intuition comes from the fact that only the effect in red is present. Now, the fun part is when orange and red are playing out at the same time. So here you have a boom bust result. So, and this is the novelty that is crucial to the general equilibrium with endogenous states, which is what we want to emphasize as a mechanism in our paper. The departure from Angeletos and Lian is when you have an endogenous state, you're actually able to have a boom and bust. What happens? Assume that delta is strictly smaller than 1. Assume that at t minus 1, the economy is in steady state and epsilon is positive. Then there is a rho at t, rho star and t star, such that for rho in between rho star and 1 minus delta, the following happens. Initially, you have a boom like before, so the effect in red dominates. And at some point, at a t star going onwards, you have a bust in investment. And the bust is such that you have less investment than under rational expectations, but we can also get a condition, which is the one there, where the bust is strong in the sense that it's below 0. So investment is booming and it crosses 0 and it converges to steady state from below. Okay? So what's going on here? First, team red is winning, and at some point there's so much about the overhang that team orange wins, and you have a bust. Now, another thing that is kind of interesting is that the bust here is a bigger bust than what you would have under rational expectations. Because these guys, when they are pessimistic, they are excessively pessimistic. Because they do not anticipate by competition neglect that other firms are also cutting investment. So their return expectations are excessively pessimistic. And so, if you were to run a simulation where you start off from a situation where there would be a bust under competition neglect, so a KT and AT such that there is a bust going forward, and you run the same simulation with rational expectations, the bust under rational expectations would be smaller than under competition neglect. So competition neglect gives you these very sharp dynamics in the investment. So, all right, let me move on. I hope this was useful to kind of like get some intuition. Let me move on now to RBC. I'm gonna have to go with a brief setup description, brief overview of the solution method, and the setup is going to be very standard. It's just RBC with sprinkle in competition neglect. And then I want to focus on the results. So we're going to embed competition neglect into a canonical RBC model, maximizing agents, the economy buffeted by shocks to total factor productivity. The novelty here is in the specification of the capital good producing sector, we're going to have these behavioral firms that have this computational neglect problem. We introduce adjustment costs. We want to have Q theory. And otherwise, we're going to follow Greenwood-Hansen closely, actually. So this is going to be sort of kind of just mixing the two for the specification of the computational neglect bias. So this should be obvious by now, but just to make sure to emphasize it, in none of the results going forward, I'm going to use other frictions. So this is just the pure behavioral friction in action. There's no credit frictions, no nominal rigidities, obviously, and also no search frictions or any other frictions. Okay, so a little bit on the model details, separable preferences, log-log, Cobb-Douglas technology, competitive final good producers with flexible prices, a competitive labor market, a single shock, which is shocks to the level of TFP, AR1, and the investment wedge is endogenous. That's important to keep in mind. And compared to the Greenwood-Hansen paper, in general equilibrium, there's like two things that are going to be a little bit a technical challenge. One is the interest rate is endogenous. It's fixed in the Greenwood-Hansen paper. And two, the rental rate functional form is determined by the production function. Okay. In Greenwood-Hansen is set up as linear. Here's going to be nonlinear, and so that we're going to have to deal with. So maybe just a phrase to address what Marty was curious about. So GDP, is going to enter in the interest rate, but the interest rate is going to be priced by the household without the friction. Okay, where the firm is going to make the wrong inverse is about the productive or capital. At a high level, what's going on here is that we're solving for some like small k, big K problem, right? You've seen something like that in the past. It was typically done with rational expectations. Here, what the game is, we break rational expectations and we do a small k, big omega k kind of problem. And then the trick is to figure out, like formally, this is what we do in section 2 in the paper. Happy to talk more about it. We formalize what this means and how we get a recursive fixed point equilibrium that makes all of this internally consistent. So to solve the model, we lock linearize on a steady state. And so here's the first result. So investment wedge dynamics. So the exercise here is we look at the dynamics of real variables in the computational neglect RBC model, and we want to figure out what are the wedges in a rational expectations prototype model that are observationally equivalent. Okay, so basically I try to give my graph and business cycle accounting exercise. And this is what we get. Computational neglect is observationally equivalent to an investment wedge, tau IT, that depends on the state, capital, and product and TFP. This is to say all other wedges are zero. So computational neglect only distorts the investment equation. So there's only an investment. This shows up as only an investment wedge. And what's important also, and I think crucial for us, is that the wedge has an ARMA 2-1 representation that you see there. Okay. And the economic interpretation of this is that this is what gives the rise to the boom-busting investment. So to understand what I'm trying to say here is imagine that the wedge had turned out to be AR1, as in the wedges in Tarek and McGrath. Then you would not be able to have a boom-bust. Here you have a boom-bust, and it's kind of especially clear because of this minus sign here. So basically, that embodies this overhang effect. So basically, the wedge acts initially like an investment subsidy, and over time like an investment tax. In a figure, so here's a simulation where we want to examine what computational neglect does in a plain vanilla RBC. This is what it's going to be doing. We're going to compare rational expectations, computational neglect. Of course, if we wanted these IRS to look more empirical, realistic, we could add bells and whistles, but that's not what we want to do here. So we want to stick to kind of like plain vanilla RBC just to try to understand exactly what it is doing. And this is what we get. So this is a simulation of the impulse response functions to TFP. In blue, you have rational expectations. There's no investment wedge, correct? However, in red with computational neglect, you're going to have a boom-bust investment wedge that is going to generate a rise in investment that is very sharp, and this is going to decline also very rapidly. That is the bust. For completeness, I'm showing also the other IRS, but let me just move on to the perhaps more interesting result. On the financial cycle,
Just one
yes,
quick question, just
Yes.
because I'm surprised that the C is going up in a hump-shaped manner. I'd like to talk about that later because that's a holy grail.
okay.
But you don't have to waste time.
Okay, it's the slight crowding out because of this big boom in investment, and it will revert, it goes up, but
Households also have the same wedge,
no, there's no wedge on households.
but they need to fork to decide consumption and therefore determine interest rate, they have to know.
Households know that firms have investment consumption neglect, and there's no wedge on that.
I see.
So just to be clear, the friction here is really only in the capital goods sector, which is, I think, kind of like what we did is
So then the hump shape is given by the adjustment,
there's no adjustment cost.
you said.
It's given, sorry, there is adjustment cost, sorry, yeah, sorry, I misspoke here. There is adjustment cost. The hump shape, maybe we can talk about it. I think it's given by the crowding out of the investment boom over there, because this is RBC, right? Financial cycle implications. So we're going to define stock value and returns. The stock value of the firm is the discounted present value of dividends. Because the firm is behavioral, the expectation here is going to incorporate the bias. And the return of the stock is the ex-dividend change in the value. And so here's the result that we get. The investment wedge is tightly linked to excess returns as perceived by the econometrician. That's the equation you have here in red. So on the left-hand side, you have the expectation of the excess return away from the real rate as perceived by the econometrician. And on the right-hand side, you have an expression that depends on the wedge. So what's going on here? Let's kind of like to understand what this is saying. Let's suppose that there's a positive TIP shock. The value of the firm goes up, firms invest. And they invest with competition neglect, they invest by a lot compared to rational expectations. Okay. So that translates in a negative wedge. So this tau IT is negative, meaning that the econometrician is able to forecast negative excess returns going forward. So notice the mechanism here is firms do not perceive these excess returns, but their perceptions are distorted. And so in reality, actually, there's equity premium from the point of view of the econometrician, where high valuations predict low future excess returns. Can I show the simulation, then I take your question? Dejanier, thank you. Okay, so in a simulation, you can see it this way. So this is the IRF of these financial variables to a TFP shock. We're presenting here two different alternative valuations of the firm, price dividend ratio or Tobin Q. So in both cases, there is a boom and bust. So notice under rational expectation, there's also an increase and a decline because there has been an increase in TFP. But because of the friction, the valuation goes up by more and it busts as well. And so notice this volatility of valuation connects our paper very closely actually to the Schiller 1981 approach for stock price for finance, which is something that we didn't realize in the beginning and took some time to understand. So this is basically a Schiller 1981 paper. Okay, and on the right hand side you can see the equity premium, realized equity premium, where the rise in firm valuation given by the bias implies a negative equity premium that remains negative for a while and then turns positive. Dejanier, go ahead.
Yeah, so the expected excess return that you showed, I guess, is from the point of view of the firm, right? So the households, because they're not trading the stock, so because I guess there's a difference in beliefs here, right? So then
Yes.
it's evaluation from the point of view
Of the firm. And so we have a big family assumption where that separates very cleanly at the level of the household, so the ownership of the firm and the valuation of the stock from the pricing of the bond. But we can go more in detail into that. Okay, that's kind of part of all the, yeah. So yeah.
Can you go back to your assumption?
Yeah.
Yeah, so here we assume the stock market operators are as naive as the firm. It's probably a bit too strong. Maybe they're not fully rational, but having an omega stock market for the stock market participants seems better.
So the assumption, that's a good question, thank you. So the assumption is we're pricing the firm from the point of view of the owners. We want to kind of keep it simple, and that's kind of like the first thing that seems natural to do here. If you want, you could imagine that, if you want to invest in the firm, you go in the building of the firm, you look at the books, and you get sort of infected with this enthusiasm, and you get infected by competition a bit. That's kind of like the point of view, the perspective there. And like I said, we have a big family assumption that makes it so that this is an equilibrium pricing.
No, but related to observable like stock market predictability and the like, you at least you want to entertain possibility that there will be an omega, a special omega, maybe fully rational, maybe it's less than fully rational.
We could do something like in the Shimshek papers where, there's somebody that wants to short these stocks, and it doesn't have fully deep pockets, and you have some limits to arbitrage. I mean, we want to sustain this kind of like Schiller 81 kind of world here. That's kind of, but I think those are excellent questions. Okay, so we can talk more about them if that's okay. Now, why is it what?
You can just price them. Their investment decisions are their investment decisions. Just price it.
But that's exactly what we're doing. So the one who's investing,
That's pricing according to the firm. We're also pricing according to the house.
which we're doing at the same time because we have this big family assumption. Let me talk about how that works, okay? Later. So there's perfectly risk sharing. There's the household is dividing in a bunch of firm owners, and then the head of the household prices the bond. Okay, so why should we care about this? Can you do the same thing with exogenous wedges? So investment shocks, a la Hussein Primicelli Tambalotti. I'm gonna go very quickly here, show how it compares. Here we're comparing our endogenous wedge versus an exogenous wedge that is driven by an investment shock. And we're doing it in a way, in red, so that's the rational expectation economy driven by the investment shock, such that the impact effect of the shock is the same on the wedge. So you're gonna see in the standard sort of like specification of investment shocks, this AR1 downward sloping dynamics. And the key thing that I want to emphasize here is that the investment shock implies a negative co-movement between investment and consumption. That is well known. And a negative co-movement between investment and Tobin skew. Why? Because the investment shock has done nothing to really change the valuation on impact, at least, of the firm. However, you've made investment more efficient. The capital stock increases, and so Tobin skew falls. Different from our endogenous wedge, which leads to the positive co-movement between these variables. So moving towards the quantitative exercise, the fuller quantitative exercise. So here, what we want to do here is to figure out how to discipline omega, this computational neglect parameter, and kind of show how far we can go with the model in terms of matching these financial moments. And so in order to do the former, we're going to bring in survey data from these forecast error regressions that Bordal and co-authors ran in their macroannual paper. I'm going to tell you in a second a little bit more about what that exactly entails. And then, in terms of results, once we do that, we're going to discuss the ability of the model to match, in a quantitative sense, stock price volatility and return predictability moments. So this is the Bordalogen, Aioli, Laporte, O'Brien, Schleifer macroannual paper. What they focus on is growth expectations of earning per share expectations. And we're going to take from these long-term growth expectations over the next 5 years. These are firm analysts that follow a subset of firms, and they give answers for this LTG measure. I'm gonna abbreviate by LTG, long-term growth, in the IBES survey. This is the regression. Define the forecast error as the answer in the survey. So the forecast error at horizon H, compare that to the realized growth 5 years going forward. So 20 quarters. Okay. And so they run this regression on LTG at time t. And what the finding is that there is positive coefficients going roughly. So on average, positive coefficients. One exception is the last quarter, but positive coefficients over a year and a half. And this is what we're going to focus on to be able to capture some sort of idea of a persistent sort of like financial cycle level of over-optimism. So, rational expectations predicts that this full information rational expectations, FIRE, predicts that these coefficients should be 0, because something that is in the information set should not be able to predict forecast errors later on. These coefficients here are positive, which signals over-optimism. So when LTG goes up, these forecast errors goes up in the sense that they go up by more than the actually realized growth exposed. And so the other thing is over-optimism is highly persistent, or probably a mouthful. It's persistent, so it persists over a year and a half, kind of like our idea of what is kind of like a short run, medium run horizon. And this is what we're going to target, the number of 2.05. Now, because this is expectations over 5 years, and this is high, is somewhat persistent, there's no hope to do this with a TFP shocking levels. So we're going to do this in growth rates. That's the only modification we're going to do to the model. We're going to introduce growth shocks, so AR1 in growth rates for our TFP process. And this is what we get. So in this table, you can see in the first panel, targeted moments. And in the second panel, you see untargeted moments. Mario.
Just a quick question. If you had an AR1 in growth rates of the standard RBC model, this is off. If you had an AR1 in growth rate in an RBC model, wouldn't you naturally get some hump shapes? So it's not an innocuous change. Larry Cristiano has a bunch of things on this, but that really matters if you have levels or growth rates for the impulse. So you're doing something important. I'm not saying it's wrong, but it's really important for any numbers that come afterwards.
You're correct. So just one thing is, we are not going to target the hump shapes of the real variables here. We're going to target the forecast errors. And so even with rational expectations growth rates, you wouldn't get that. And second, just to clarify, what I showed before was with levels. So this hump shape that you pointed to before, sorry, let me just show it again. This is with an AR1 in levels. Okay? Just to clear.
But the RBC thing would be quite, the RE would be different. There you would probably start getting hump shapes.
That's fine. But that's fine. But so our goal here is the forecast error. And we're gonna get this just kind of as a little bit of a plumbing kind of exercise to kind of like make sure that we're broadly in line with the dynamics in the data. So, and then we're gonna show this is what we care about. Untargeted moments for financial things, including excess returns and return predictability. How much time do I have left?
8.5 minutes.
I go until 10. Yeah, okay. So
Sorry, that's, one question.
yes.
Oh, pardon me.
Sorry.
About the untargeted moments, it seems like a relatively cheap one that would be worthwhile checking would be just doing like a standard business cycle accounting, measure the investment wedge in the time series and benchmark against that. And in particular, in doing that comparison, that could be a good place to try. I mean, all your untargeted moments too, but it's not obvious to me why we would go with this particular expectations formation process, like horse racing yours against diagnostic extrapolative expectations, other like widely used expectations would be helpful for.
In our previous paper on diagnostic expectations with Sanjay, we did a diagnostic expectations in RBC and it gives you dampening. So it goes the other direction, but I have to talk about it. So it just doesn't work. Okay, so with discipline omega to 0.04, we get roughly to this 2.5 as in the data. We're going to use parameters of the process for TFP to match things like mean output growth, standard deviation of growth, autocorrelation. And then standard deviation of output growth, we're going to match with the adjustment costs. Now, the really thing that is novel here is that the model calibrated like this, RBC with no other frictions, does a good job at matching these two measures of propagation, Tobin skew and price yielding ratios, its volatility, and excess returns as well. So it goes, we get about 3/4 of excess returns that's in the data. Notice, real rational expectations model would give you 0 here. It would give you much less volatility here. So you would be really off, and it would give you 0. No excess returns. Okay. Because rational expectation doesn't predict excess returns. So to kind of go deeper into that, we also can match, roughly speaking, return predictability regressions, which is what this is showing. So these are regressions of for different horizons, years going forward, of the excess return using current Tobin skew as a regressor or price yielding ratio as a regressor. In the data, you can see that there is this downward sloping pattern of these coefficients in this regression in both cases. And the model roughly is, ballpark, doing a good job at it. Notice rational expectations would be flat at 0 all the time. So we completely miss these moments. So that brings me to the conclusion. So we think about this paper as bringing in another tool for the macroeconomics toolbox. The key feature of this tool, this behavioral friction, is that it appears to be quite useful to generate something that has been difficult to generate, basically connecting the real side of the economy and the financial cycle in a way that they're deeply interconnected. So the way it works is the friction implies an investment wedge that takes care of the real side, but at the same time implies these distortions in expectations that generate these financial cycles. And you have a movement between the two. Thank you very much. Let me take questions, please.
So very interesting. The boom bust part, the bust part relies the AR2 being negative. Requires an exogenous persistence, right? So without the exogenous persistence, you get the monotonically decreasing. Did I get this correctly? And do we have some intuition for this?
Yes, the answer is that's an excellent question for it. So it's actually fun. So we had a lot of fun with the toy model. What happens is when you have an IID shot, I think that's your question, right? Is you don't have enough of a build up of capital. So you need to have this sort of like right parameterization of modulation of these two effects such that they don't kill each other. So something you would get actually with AR1 shots is isolations, like in the memory is blanking like this, the cobweb model. You had isolations, right? In the capital stock. In order to get this clean boom bust, you need to have some persistent dynamics that build up the capital enough, and at some point you're not passing. So that's a great question.
So that was, if I have roll to zero, I get like.
You get isolations.
Oh.
This is why the conditioning wall was there. Yeah. So it's kind of it's very closely connected to the older cobweb model, but here what we have discovered is a way to get this boom bust.
But it's all because you see capital for depreciation, capital. You see your competitors' investment through their capital depreciation, because you see capital.
You see capital today. Yes.
So that reveals the shock yesterday. That's why it's an AR2.
So the shock is AR1.
I know, but the representation.
Oh, yes, yeah, exactly. Oh, yeah,
You
yeah,
see the
okay.
shock from yesterday.
I think Saki have better intuition than I do about this. So there's an AR, but you know, it's like you can tell by playing with it. Yeah. Yeah. Other questions?
It seems that the way this is the strategic sustainability is kind of similar to the way that like common knowledge launch point. And if I had lack of common knowledge in an investment model, but it's similar, or how would this model look different to that?
So we don't know the answer to that, but I think the answer would be yes. Because like I said, you know, the latest the Young paper is fantastic paper. I mean, they discussed a wide range of, and they show that they under some conditions are equivalent. And so I think my conjecture would be if you do substitutes in an investment model like this, and you do this and you do it with lack of common knowledge, you would be able to get the same thing. Perhaps it would be less tractable. I don't know. Right, the key thing that the way it's set up in Greenwood Hansen that we like a lot is that it's actually really tractable and can be done in general. Yeah.
What's the interpretation of, so I think you calibrated the omega parameter for 0.04. What's the interpretation of that? Is it 96% is miss?
It's a strong degree of neglect. You know, if you think about it literally, it means that, you know, you're just looking at 4% of the other firm's investment. Maybe think about it in the people you go for dinner or for drinks, you know, in your industry. I don't know. You can also think in different ways, right? I mean, that's a good question. So we haven't really literally interpreted that. But you know, the point is what's going on in the data is that this is a very strong degree of overconfidence. So, you know, being above 1 for this coefficient already means overconfidence. Being above 2 is super strong. So this is just what the data says, right?
We're almost out of time. So last
Yeah.
thing, this is the anti-Schleifer JPE paper, right? Andre wrote a very important paper in the 80s on investment booms were times where everybody was optimistic.
Limitations.
Exactly.
Or the 82.
And I'm not saying this is better or worse, but it's very different than Andre. I just leave it at that. Also, for future questioners, this is not just for ballast. You have to turn it on.
So now you can tell me why is it so different.
No, because the essence of Andre's thing is the multiple equilibria. I'm gonna invest if I think you're gonna invest, and therefore GDP is gonna be high, and so then we all do it.
I see.
You have a fundamentally different mechanism, which is not a good, per se, a minus or plus, but it is fundamentally different than Andre's. Bill Dupour, I should say, also had a very similar paper.
So I need to read that paper
It
again.
just is what it is.
Yeah.
Okay, great. Well, thank you very much. Thank you. Mike is going to. Thank you very much. Mike's gonna handle the timing on this one. I have to step out 10 minutes early, then I'll be back. Nothing personal, and Fernando, you're on that.
And we should be good to go, yes.
This one. Checks it out, sorry, that's it. You wanna remove the bar? So I want to, yeah.
Remove those of the controls. Thank you.
Yeah, Alright, so I'm gonna do some, piece of paper with a young, energetic, author that knows a lot and be very valuable. So, anyway, so, here's a, oops. Once and then, or every time? Or-
No, if you,
Okay.
it should.
They really cut the funding, even for the kids. Like what? Okay, so I just now go through like a summary with some notation. So just like call it out. All right, so we're gonna start with like a linear quadratic problem, like the ones that we used to study in school. Like for a single agent, imagine for a single agent with some idiosyncratic shocks. And then we're gonna turn it into a game, kind of like monopolistic competition type, in which every agent is very small, by having some interaction terms. So the interaction terms are gonna be theta x and theta a. With a minus, don't ask why. We do minuses so that then things are in mathematical. So minus theta x will be like the cross derivative between your own state and the average state, the state of everybody else. Minus theta a will be the cross derivative between your own action and the average action of everybody else. That's the sense in which you're not solving an individual agent problem. And then these two things have to be kind of square with each other, have to be consistent in equilibrium. So I'm gonna define that, but that's it. So these are matrices, but you could think of this as a scalar. Okay, so, and that's a sense in which will be strategic complementarity on the payoff between the, in the period payoff, between the actions or between the states. Okay. And so then we're gonna define as some sort of game, it's a dynamic, so it's gonna go through time. There will be some state that is initial, you choose actions and then things will evolve through time. And the equilibrium from the game will also solve the same type of equation that the single agent problem solves, which if you study with my young co-author the book, like this Riccati equation. So the Riccati equation is for maximization, but it turned out to be that under this assumption, the same type of equation describes an equilibrium. Okay. And then the equilibrium actually exists. If it exists, it's only one. But it exists if there's a maximum amount of strategic complementarity in both of them in a way that it can be sort of sorted out that admits an equilibrium. Once there is one, if it admits an equilibrium, there's only one, and that's because of the linearity. Okay, so now so we're gonna compare like a single agent Riccati equation, which will be like, suppose you have this model with no interactions, so everybody's doing their own thing. Then there's you can aggregate and compute the average action and the average state. We're gonna compare that, and since it's a dynamic problem, it kind of you need to solve the value function, blah blah blah. You need to solve it. We're gonna compare that single agent Riccati equation with the one from the equilibrium. Okay, and how is that they differ? They differ in the following way. You take a look at the second derivative that you use on the period joint function for the single agent. Let's call it Q. This is a typical notation in my author's book. You call it Q, and then that will go to Q plus theta x. So meaning that if you have a strategic complementarity, so this is negative, then you will have less curvature. So less curvature typically means that you don't mind being away from a steady state, and then it will have implications for persistence. Likewise, if there is a strategic complementarity in action, the equation that describes the equilibrium will be one where the curvature, instead of being the single agent curvature, will be the single agent plus this other matrix theta A. So if there is a strategic complementarity, this will be negative or negative definite. And that would mean that there is less curvature, you can suffer less by changing your actions. Well, actually, that means that you change them a lot. So then you tend to actually have faster convergence. So the implications for convergence for persistence is they are the opposite for strategic complementarity in states and strategic complementarity in actions. And in fact, then we're going to look at, for instance, do the comparative study of either this matrix theta x and theta a by taking a matrix that is a bit more, whose differences are possibly definite. That means that it's bigger. And then we'll see that they map monotonically under certain conditions into the eigenvalues of the system. And the same with the one from the states, but with the opposite direction, meaning that more strategic complementarity on states, it means that you are more persistent. Your eigenvalues are closer to zero, less negative. More strategic complementarity in actions, then the eigenvalues are smaller, more negative. You go faster. Okay. All right. So then we're going to compare the utilitarian planner with equilibrium. And the utilitarian planner is an awesome planner. It could boss people around. Many of us have been in this type of situation that they boss you, they tell you what to do, whatever. So that's the type of planner that we're going to look at. And then the planner problem, it will take into account all these externalities, but it turned out to be that it's the same as solving an equilibrium with twice as much strategic complementarity or strategic substitutability. It's kind of, in this setup, it's kind of trivial why this is true. The idea is that in an equilibrium, you think about what the others do, and then you do this. But the planner, think about, that the others affects you, but it thinks that you affects the other. And because of the linearity, you just multiply things by two.
In fact, what you do is you add a matrix plus its transpose, but given symmetry, you multiply things by 2. It's kind of an obvious result, but it's true. And together with the previous results, it tells you that if there is a strategic complementarity in states, then the planner will likely to go to steady state even at a slower rate. And there is a strategic complementarity in actions, the planner will likely to go to the steady state even faster. So this kind of follows from the previous one. Yeah.
You're gonna give some example.
Yeah. Yeah. And then we're going to look at this economy because of the linearity. It's kind of imagine that you have some data in which you have aggregates and you have idiosyncratic observations. And the idea is that if you neglect the aggregates, there's nothing that you could learn about these two. Or let's say if you put like time fast in your regression, you basically throw absolutely all the information away. It's kind of like a simple way of seeing a version of the generalized missing intercept. At least kind of level generality. And if there's time, we'll talk about like sort of more nonlinear ways in which the interactions are not time and interest. The interactions are not just with the mean, but with the second, third, fourth moment of the elements. There are some results that extend to. Okay, so some notation and then I'll do some. Sorry. So the notation, I think it's easy. Well, I don't know.
Maybe just for the first slide,
Yeah.
say like, we're all familiar with Kimball, that it's the state
Exactly.
pickup, and then we know that result.
I'll do Kimball, yeah, as an example.
And then for actions, I don't know if there's an example.
To me, actually, it's much more clear. The main examples are with states, sorry, with states and not with actions. But for instance, I'm gonna do an example in which you have, say that you are investing, and then the price of investment, you're facing an upward sloping supply curve. So that will give you that then the price of the investment good will depend on the aggregate action which will be invested. And then in that case, it will give you strategic substitutability on the action. Yeah. But you're like totally on point. All right, so notation is, this is the period return function. It has some quadratic term on your state, some quadratic term in your actions, some interaction between your state and the average state. That's the definition of the average state. And some interaction between capital alpha. I know it's good that they're not Greeks, but I know it's not a capital alpha, it's a closest we could do. Capital alpha, and this, by the way, there should be like a capital alpha that doesn't look like a negative. So well, I'm gonna call this capital alpha. Okay, so capital alpha. Okay, so and capital alpha will be, well, imagine that if you have the optimal action, it will depend on the state of each person, then you add it up across a cross-sectional distribution and this I'll develop the notation a little bit more. So little x is your state, will be a vector, capital X is a vector, these are your actions, and then capital alpha are the actions, and M will be a cross-sectional distribution. And then there'll be some matrices with the idiosyncratic shocks. Second, on derivatives, interactions.
Sorry, Fernando?
Yeah.
Yeah, I'm missing something. Why no interaction between little x and little alpha? Like if I'm hungry,
Yeah,
I want to
yeah,
eat more.
yeah.
But
These are the ones that come out nicer.
no, but can you handle that? Or
Yeah, they
supposed to
don't
handle
have
some
the-
interaction?
They don't have no, but
My
yeah,
state,
we looked
but
at
I-
all sorts of examples.
Okay.
These are the ones that have a structure that kind of so nice. That's it. That's the actual reason.
Because otherwise it's just no structure.
Yeah, so when I get to that, I'll tell you the part that makes things to be very, we think that it makes things to be very simple and nice, but it will be worse. That's what I mean. But I'll point it out. I'll point out one more that we explore and doesn't quite work nicely. Okay, and then your state evolves according to B is a matrix times alpha minus A times S. This is typical notation from the linear quadratic problem. So this will be your grid. And then there is some Brownian and some various covariant matrix of the Brownian. Okay, so now I'm gonna write down the maximization problem. So not a specific heavy notation, but it is what it is. So I have you, I'm gonna close the doors and then go through the notation. So this is a Hamilton-Jacobi-Bellman equation. So rho times u, it depends on time because this agent is taken as given the path of x as well as the path of capital alpha. And because of that, at the very end, we'll have a derivative with respect to time. You will have a second derivative with respect to the axis because of the Brownian. Then you will have the period return here, the interaction, and then all the other terms that has to do with your optimal choice, I'm gonna group them in a sort of indirect utility function in the Hamiltonian, this object here. So this is just a way of splitting the problem in two. There's nothing. So this Hamiltonian, it's sort of like if you plug in here the value of the derivatives of the value function, is sort of the continuation part that I didn't write down, but it's useful to write it this way. So this will be, say, a vector of all the derivatives. And you're trying to do the best with your R. Let's say this is with the cost of your actions. This is the vector, the shadow value, if you have a little bit more of your excess. And remember, you have this sort of cross term here. Okay. And this Hamiltonian will have an optimal alpha. So alpha sub star that depends on P and A. Doesn't depend on it. And then the drift, when you plug it in here, you will, so notice, remember the envelope from like the micro type of thing, the envelope. So the derivative of H with respect to P will be this, evaluated at optimal action, that will be the drift. Because the Hamiltonian has basically all the part in which there is some maximization. So the partial derivative with respect to P, if you were to evaluate on the optimal action, it's going to be the drift. That's why the Hamiltonian is useful to do this characterization. You will see it in a second. Okay. So that's his problem. So that's kind of half of it. That's maximization taken as given this path with this path. Okay, we're gonna put some assumptions. So the assumptions are such that if you didn't have this term, which is interaction, and if you didn't have this term, this is a well-defined problem. So like, it's a single agent decision problem. We would like this problem to be well-defined. So we put assumptions, so, concavity, this type of assumptions. So these are the standard assumptions. So that the linear quadratic problem is well-defined if you didn't have any interaction.
Fernando, can you clarify again why T appeared?
Because, see, you take as given the path from the game, it's like a monopolistic competition. From the game, you really don't care about what every person does. What you care is ideal price index.
Yes.
But because the problem is dynamics, you need to take into account the whole path of the ideal price index, let's say. So that would be maybe this object in Kimba, like Ivan was saying. And also the path of reactions. And because of that, then you write it as XT. We could have written this as with a density, but that's a more difficult. It's a more difficult. Yeah. Okay, so it's like an impulse response sort of thing. So if there will be no interactions, then this will be a sort of, it will not depend on time because it's just a recursive problem. It will not depend on anything. So we put the assumption so that this is a well-defined problem. Okay. So now the second part is, now the notation is a bit more pedantic here than when it needs to because of the part in which we go through higher moments, which may or may not have time or maybe interest for it. But the notation here is you take the cross-sectional density M and you think about it in a point, this is the time derivative of that. Well, we'll have a second derivative of M with respect to X. And then we'll have this term. So this is the optimal drift. That's why it's kind of nice to use a Hamiltonian. Because HP is the optimal drift if you plug in the derivative of the value function. So if you ever done continuous time maximization, you will recognize this. If you have not done it, you have to take my word and that's it. I mean, there's really no, if a non-convexity problem. But this is kind of like the micro. This is the shadow value, which are the prices, which are the derivative of the value function. You plug it into a Hamiltonian, which is a known function, and then you get the drift. You take the product of the drift times n, you put a minus, and you differentiate with respect to x. That's the drift of the Kolmogorov formula. That's a formula for the Kolmogorov formula. It's weird. It is what it is. That's just physically, it's just a Kolmogorov formula. in several dimensions, it's called divergence, it's slightly different, but think of this is what it's saying is you differentiate with respect to x, and then you put a minus. Okay, so that's the other part of it, the aggregation. Notice that what is nice of writing it this way is that this makes direct contact with the value function. That's essentially the game, so that's why you just use a Hamiltonian. And then to make this to sort of that what people think that it will happen is, sorry, I had to apologize, so we're using rational expectations. So, but anyway, so in this case, this xt is the xt that occurs at every point of time, and the at is the action that occurs at every point of time. This is a bit cumbersome, the action, because to recover the action, you need to across people, you need to add kind of the action which depends on the Hamiltonian, so it's a bit of a mess. It's a little bit of a fixed point. Okay, so in equilibrium, it's just putting these things together, so I'll just put everything together in one slide. Two partial differential equations is two, but it's super simple because everything is linear quadratic. The one from the densities and the one for the value function, they are related to each other because in the one from the densities, you have the x and the a. And in the one for the n, you have the derivative of the value function. So they're kind of coupled together. And then the definition of the Hamiltonian, this is a trivial problem, as a quadratic linear quadratic problem. And then when it makes the interaction expectations, is 2. And this problem is defined for an initial m0, and it has, it goes forever. So there's some sort of boundary condition for an infinity, some sort of transversality looping condition. So is that okay? So this is sort of, but it is what you think that it will be. Like, you maximize taking as given this path generates a density, the two things are consistent with each other, there's a bit of notation we could disregard. Okay, just a definition, I'll give it to example, sorry. So the cross derivative between little x and big X, this is, when this is negative, we say that a substitute. When this is positive, we say that a complement. But we put a minus before. It's just notation convention. Okay. So strategic complementarity would be like these guys without a minus is negative. Okay. And the same for the actions. Okay. So positive derivative, positive cross, complementarity, negative cross. Think of this as matrices now. That's kind of difference. Okay. So let's go through an example. Well, that's example that I just. So think about an example like a Tobin's cube, like in the previous paper. So think about like a Tobin's cube model, but when you produce a differentiated good. This differentiated good, sort of, you're a monopolist. You sell it to the typical constant return to scale sector with a big sales ticket. Because of that, there will be strategic complementarity coming from like the Blanchard-Kiyotaki effect on the demand. That if everybody else has a lot of capital, that produce a lot, that pushes your demand to the right, that will turn out to give you a cross derivative that is positive. But suppose that the price that this sector pays for investment relative to the numeraire, it's an upward sloping function of total investment, which is investment will be the action, then there will be a strategic substitutability in actions in this very, very simple problem. So this is a problem where you have both strategic complementarity and strategic substitutability. Strategic complementarity coming from the demand externality from the CES and the diffusion return to scale. And then the strategic substitutability in action is because, so if you really invest a lot, then capital investment will be high, then the price of investment relative to the numerical good will be high. That's not good for you. Because to get a given investment, you need to use more resources. So I think this is like a totally fantastic problem. And then, of course, you need to guess where is the path of the ideal price index, and you need to guess where is the path of the investment good, and that's why this is some sort of game. But second example, which is the one that Ivan sort of anticipated. So this is a multi-product version of Kimball. So imagine that you have n products, and then you have a CS between your n products, and not necessarily symmetric. I'll tell you why I want to think about this case. So think this is a store. So you send them products. They aggregate it into CS. That good then enters into a Kimball demand across stores. Okay. So you're really selling a bundle of goods. You're not selling a one. You put it together in CS, non-symmetric across goods, and then you compete with other stores with a demand without constant elasticity. So that example then will give you that example will give you a strategic complementarity on the stage, just a way that Ivan sort of I guess it. The thing that is nice about the example with a multi-product group, okay, and let's say the price adjustments is like in Rotterdam. So it will be a quadratic cost in the rate of adjustment, so that will be the alphas. And the state here will be the price vector. And you need to think about the state of the other ones because your elasticity depends on your position in the demand, like you keep them. Now, even though the goods are not symmetric, this cross derivative will be symmetric. So these assumptions that these thetas are symmetric, in some examples that we worked out, we were surprised. We were using them because of mathematical convenience, just to be fair, to be truthful. But it turned out to be that in several examples, they do come out. So even though there is no symmetry across the products, this will be symmetric. It's not quite quasi-linearity, but it is something related to understanding the structure of demand, something that we'll learn also in our talk today. All right. So now let me construct the equilibrium. So I'm going to construct this. I'm going to do maximization, aggregation. I'm going to do this graph that depends on when and where you were to grad school, you have seen them or not. I won't do the graph, but you know, I did graph with arrows and things, and then things, okay, with the things diagram, I'm going to go through that. I was in the right time, but in the wrong place to learn these arrows because they were forbidden. This continued time we said at the time. But anyway,
There was a fatwa.
exactly. There was an indictment by my advisor that you should not do continuous time. So okay, so I'm gonna do the first maximization, then aggregation. I'm gonna put it together in some sort of graph like this, and then the solution for the saddle path will be a quadratic equation. There will be some sort of Riccati equation. First, it looks awful, then it looks great. That's kind of it. So let me do it. All right. So first thing, there is this Hamiltonian. This is literally a quadratic problem, not like a dynamic, a quadratic problem. I just reminded you of this. This is like trivia. You could solve it by have linear demands, linear options, and then you could plug it back and it's quadratic. So everything is in gray because I don't want to tax you with doing this. This is trivial. This was trivial even before Claude, so imagine. But the point is that the optimal actions are linear, and this is quadratic, and this is linear in X and 2. Fine. Second, how is that the value function is going to look like in equilibrium? It's going to be quadratic. It has to be quadratic in X, but with coefficients that change through time. Why? Because this is a linear quadratic problem. The only interaction is that say you are given by things that is changing through time, or the action, the price of investment is changing through time. But it has to be quadratic with coefficients that change through time. The coefficients are a constant, a vector, and a matrix. But these are coefficients that change through time. So you have to look like this. So now you use this information and you plug it back into the in the PD, into the value function, and then the value functions on both sides, and then you match coefficients. Coefficients that have no X, coefficients that have linear in X, quadratic in X, and then you're going to have ODE for each of these. Why ODEs? Because these are functions of time, so they are time derivatives. Okay, so these are the ODEs. Again, these should be in gray in the sense that I don't want to tax you to read them, but the point is that there is an ODE for beta 0, scalar, an ODE for this vector, beta 1, and ODE for this matrix, beta 2. Now let's look, and this is taking as given the path of capital alpha and the path of capital S. We're taking this as given as of now. So it's a forcing variable. Sorry. Yeah, I'm not that two-dimensional. I'm really three-dimensional. I see that you couldn't see. All right, so let's look at this one. Take a look at this one. This one doesn't have theta. So this is the same Riccati equation from the single agent. So we know the solution. it will be the second derivative of the value function, and it will be constant through time. So this is one we have under the bed. This is a solution that depends on Q, but it doesn't depend on anything about this path, nor about this matrix theta. So this is our all good friend. Now let's take a look at this guy. Well, this guy doesn't have beta zeros. He has some beta twos, but we know that they are a constant that we could solve already. And he has some capital X and some capital F.
Wait, to establish that it's a constant, you have to also make a statement of terminal or initial conditions.
The only way for this problem to have final value, so the assumption that I gave you were that the problem was concave, then the only it works. I asked my junior co-author and he told me it works.
Okay. I trust.
So if you look at the, let's say, all the other ones explode. And they make the beta zero, I'll come back to that.
Okay.
But anyway, so, yeah, there's only one solution, it's like Highlander, there's only one for this. Because there's only one solution that, well, no, I know that it's like in the Godfather 3 that you get sucked into it, no. I will contain my urge and I will not go through, okay. So notice that this one doesn't involve beta zero nor beta two. Because the beta two now is a constant. But beta zero does. So I'm gonna come back to this. So the first thing is that these things are kind of recursive. Now there's something here that is annoying, which is this capital alpha. So let's do a little bit of, let's eliminate this capital alpha. Okay, and then I'll come back to this. So capital alpha, again, this is in gray, so it's not to touch your brake sails. So this is trivial algebra. Because of the linearity of the decision rules, we could think about the optimal decision rule, the optimal alpha for a given agent as a function of the derivative of the value function and the alphas of the other agent. Everything is linear, so the fixed point that look like a scalar here would be just matrix inversion. So you end up getting this equation here. The important point for this equation is that the action is just a function of the state and beta 1, which is unknown as of now. This is something to be expected because the first order condition plus aggregation, so expected integrals that go through it. Okay, so now we're going to go back to that, get rid of this annoying capital alpha. We're going to use the equation that I just obtained, don't look at them, and then I'll obtain this one. I don't mean for you to look at it, except to notice that this is depends on beta 1 and x and nothing else. Everything else has been solved for. This is an ODE, constant coefficients. This is a vector, and it depends on these two other vectors. Beta 1 is the derivative of the value function. It's a co-state looking object. Okay? But this is an state looking object, the average. Now let's go to this. So I'm going to do this in the kind of non-rigorous way. There's some more rigorous proof. Now we're going to go through the aggregation of the Kolmogorov forward. But instead of doing that, let's just take this equation and aggregate it across people. So this will be capital alpha, this will be capital X, this will disappear because across people this will add up to 0. That's a part that can be done better, but let's say we do that. And then once you have capital alpha, we substitute the equation that we have from capital alpha. Then we'll obtain an equation for x dot. Why x dot? There's no any shocks. So the law of large numbers will give us a deterministic change on x. This is an ODE for x as a function of beta 1 and x, constant coefficients. All the coefficients there are known. So now let me collect everything. Here we have the solution of beta. Then we have these two guys that they refer to each other only. This is a state co-state type of system. And they depend on each other. This is the dots of them, and these are the letters. We could put it into a matrix, and we'll do it. Once we are done with this, we're going to go back to beta 0. Beta 0 is this scalar. This scalar is quadratic in beta 1 and at a, but a is just a function of beta 1 and x. So this is quadratic on beta 1 and x. It's solved forward. So this could kill something that is growing, but things cannot grow here too much they cannot go more than rho divided by 2 because these are quadratic. And that's why to find a solution of these games, you need that this system here, when you solve it, it doesn't grow at a rate bigger than rho divided by 2. That's the solution because that will give you a final value function. Okay, so now I'll do it. So what I'm going to do is I'm going to take beta 1 and solve as a function of x. So I'm going to make basically beta 1 a function of x. So this is the system. I just copied it again. This is a matrix. That's a matrix there. So notice something. This matrix has a lot of structure. Of diagonals, they are symmetric. Diagonal terms, except for the annoying row, which will take care of it, except for the annoying row, actually it's nice that it's there, but except for this, the diagonal terms are the same, transposed with opposite sign. So that's why there's a lot of structure. This is what is called a symplectic structure. It's an algebraic structure that comes from Hamiltonians. This is not a maximization problem, but once you look at something like this, you realize that something good will happen. Okay, so I'm going to look at now beta 1 as a function S of x. This will be a matrix. If this will be a scalar, it will be a quadratic equation. We'll have two solutions. You pick the right one. That's always a good thing to do. So let's do that. Okay, so I'm gonna replace beta 1 by S times x. So this will be here. Here, this will be S times x. So x dot will be S times x dot. I will replace one into the other one. That's why I'm going to get a quadratic equation. You see, if you ever run this in a problem set, if you're too young, you never do it because someone else will plot or someone else. But if you're old enough, you have done this by hand, or you have seen it in some book that people have done it by hand, and you get a quadratic equation. This is going to be a quadratic equation in matrices. And it's going to get worse before it gets better. This is the quadratic equation that you get. This is not nice. It's a bit of a nightmare. The equation is S, quadratic, linear terms, and constant terms. And it's also not nice because it depends on beta 2, which is itself the solution of the quadratic equation. But that's what we're trying to solve for. And then once we have x, when we have s, then we could solve for the dynamics, which will be an R1 with this vector x, that will have part of it, which is just what you would have gotten, have no interactions. And part of it is the one with interactions. So is this okay? All right. But you notice that the previous video was so too nice not to be, so something better happened. So we notice that we cannot solve for S, but we can solve for P, which is kind of the excess of the single agent part. Because P is S plus beta 2. And this one solves this matrix that is really beautiful. This equation is really beautiful. This beauty is on the eye of the beholder, but it's like your kids. How can you say they're not beautiful? So this is a beautiful equation. It's kind of very simple. It doesn't have inside of the coefficient the solution of another Riccati equation. And if you compare with this one, it has the same structure of the single agent Riccati equation. It's literally the same type of equation. This one is the one that we all learn, some of us learn, except that gamma is replaced by theta A plus gamma, and except that Q is replaced by Q plus theta S. So if you know the solution of this one, you know how it behaves with respect to Q and gamma, then you know how the solution of the equilibrium behaves with respect to Q and gamma. And that's the sense in which strategic complementarity affects curvature in actions and curvature in states. Okay, and this is a nice enough structure that you could do monotone comparative statics. So if you have like a matrix that is more positive definite, then this will be more negative definite. If you have a matrix like this one that is more positive definite, then this one will be more negative definite. So it's sort of like so you can do kind of nice comparative statics. All right, so that's the first part of what I was saying. The second part is to convert this into statements of persistence. So we'll do, well, first of all, existence. So let's disregard things that is in gray. So this is a necessary condition for equilibrium, which is that this guy cannot be too negative. This has to be positive. If this will be scalar, this has to be a positive number. If these are matrices, this has to be positive definite. That means that, remember that strategic complementarity makes this negative definite. So there's a limit on how much this could be. They could upset each other, but there's a limit to that. Okay, and we could compute what the limit is. Okay, they could be quite a lot. They could almost negate all the curvature here and there. Okay. Let me not go into this. So let me explain two notions of persistence. So one notion of persistence that works out here is the following. So you solve this problem. This is the evolution of capital X. Now take a set of initial conditions. Not one, a set of them. For each initial condition, evolve your system up to time t. Call that xt, collect this set. So this is the set, take initial conditions, evolve it, and then you will see this set later on. For each initial condition, you will go somewhere, keep track of them, look at this set. Is that okay? If these sets are in R2, look at the area of these sets. If they're in R3, look at the volume. If they're in R4, look at the Lebesgue measure, so on and so forth. So the volume of this set depends on the strategic complementarity. So when strategic complementarity in state, it shrinks at a slower pace. When strategic complementarity in actions, it shrinks at a faster pace. So this is my help from Claude. So doing the graph, I was so proud of it, but I think Ivan will do slightly better graphs. So this is the set of initial conditions. Say this is an R2 example, and then either it will shrink to this one or it will shrink more. This one that shrinks a lot is when there is a strategic substitutability between actions or strategic complementarity between states or strategic complementarity between actions. And for those of you that have physics background, you will know this because this is it's a combination of what we have done before on the comparative static and the Lewis theorem. But anyway, okay, so that's a notion shrinking. You know how close things get to the time depends on strategic complementarity and states and states and actions. There's a case in which you could almost solve it by hand. Well, one is the scalar case, in which the eigenvalue of the one-dimensional system is this, and you kind of see that these two they play opposite levels. What you would like also, you see the existence result because you would like this has to be positive so that this is smaller than rho over 2, and you see that that's why there's a maximum of how negative this could be, so this will become a complex number, and you see that they work on opposite direction. Now, if you take the matrix A to be a scalar times I, but you keep all the other ones being matrices, then this actually reads the same way. Each eigenvalue is equal to rho minus the square root of this term, the same as the term in the one-dimensional case, plus each of the eigenvalues of this guy. But the eigenvalues of these matrices, they kind of look like this. They have a q plus theta in the top, 2 square roots multiplied outside, and they have one inside. So you could do the comparative static eigenvalue by eigenvalue in this case.
But the initial set is also a function of these guys.
The initial set it holds in general even without this. No, the initial set is
No, it depends on the.
No, because remember,
Initial condition.
No, the initial condition is exogenous here because I already solved for it. It's not a state.
No, but beta 0 and beta 1 will depend on the entire.
Correct, but I already solved for them. So here I'm sorry that I was not clear. Look, I'm talking already of the system of X. I already solved for the saddle path and I'm linking X with itself. Probably I threw maybe I confused you because I mentioned Lewis theorem, which is a theorem for space of space.
Just like, I never saw a mapping from your M0 to your B0 B10.
It's this guy, yes.
Yes.
So here is here you have beta and x's,
Okay,
and then here you make the betas a function of x.
okay.
And the function has coefficient s, which is this matrix, which is ugly until it becomes beautiful.
Okay.
And this x dot is just beta. Notice it's even the same type of law of motion with the difference that is p as opposed to beta, and this is opposed to this. Sorry. Okay, so these are the results on persistence. And let me just very briefly talk about the Planck's problem. Well, the Planck problem is you take the utility function for each agent and then you add it across people. It's a utilitarian planner. And then you do the same with all the terms. So I don't really have much time to go in detail, but it's a utilitarian planner. It's not Pareto optimality. It's a particular set of weights. You give everybody the same weight. Then you solve the planet problem. Planet problem, you have to manipulate the entire distribution. But you look at an equation like this for the Lagrange multipliers on the Kolmogorov-Fogel equation, and this one, and these equations, they look almost identical to the equations for the equilibrium, with the difference that the planar has basically 2 theta's for A and 2 theta's for X. And the intuition is the one that I tried to give before, that in equilibrium, you worry about what the other people do. The planet also takes that into account because it's a utility function. But the planet also realizes that what you do affects the other one, and there's a bunch of people like it. That's why if you solve the planet for a model like this, it's the same as solving the equilibrium with something that has twice as much interval. Because you know that, then you know how this affects persistence. And let me finish, because I've probably had like a minute or not. Let's say that we add aggregate shocks, which is kind of trivial because of certain equivalent. Let's say we add aggregate shocks. And now we have a system for capital X, and we have a system for Z, which is the difference between your X and the aggregate. You could just write it that way. The system for Z is the same as the system for the, and then you have actions for someone where the aggregate is X and you're the X, and the actions for a representative derivative. The actions for a representative, notice that when, if you subtract your alpha from capital alpha from alpha, you get rid of these and you get these actions, which are the ones from a model without coupling, without interactions. And also the dynamics of your Z, which is your X minus the average, are just the dynamics without coupling. What does this mean? This means, in terms of identification, if I give you data between X minus capital X and alpha minus capital alpha, it has absolutely no information on thetas. You kill all the information that you could have had. You observe actions, there's certainly no more information on thetas. This is typically what we think about it here because of the linearity, it's just false exact. And then when we go, there's no time, but when we go through it, it's like, if I give you more information, what can you recall? Okay. So let me just stop because I think I'm out of time, but the conclusion is essentially the beginning plus trying to explain this better. Okay, thanks.
We worked for 15 minutes and start again. Thank you.
Then you are. All right, perfect.
I know, buddy.
It should be.
Okay, so anyway, thank you for having me, and I hope Larry will get back in shape. And we're very excited about this paper, joint with Weevil, and it's a kind of an outgrowth of a paper that I presented last year here. I'm still presenting that paper in now this paper, because that paper evolved a lot. And that paper will poke its head here, as you'll see. But this is a new paper with the intention of really taking that paper to answer a specific question and using it to think about macro again in a different light. So let me tell you kind of philosophical aspects and then just tell you what we do. Philosophically, kind of, I want to convince you that this is a very important book, obviously, okay? And maybe because it summarizes a ton of very important work by others. When you think about micro and general equilibrium, we go to this. And this is an important book by the 20th century. So is this, okay? And this is, an important book for everyone in this room, I guess. Of course, there's other good books like Jordi. I don't want to, but I think it's fair to say that this kind of sets the stage in micro, sets the stage in macro, but there's a gap that's left, and that's kind of what this paper is about, talking about that gap and filling it, okay? And that gap, here I have some slides saying it, is like, you look at general equilibrium theory, and it's this simple theory that's expressed in a very summarized way by, let me put this like that if I can, by, an excess demand function that's mapping from n prices to n excess demands, and you set it to 0. And you work in that way, in a flexible manner. Of course, we're not here to do theory for theory's sake. It's got tons of applications, okay? Both positive and then normative if you think public finance. And that's, but it has this common language and this simplicity that comes with being general, but yet being general with a very simple principle that then lets you be simple at the same time. I always tell my students, if you manage to solve this problem in a very general way, it might be simpler actually. Because if you find a way to solve a problem that's general, it must be you found the angle that makes it all trivial, okay? And that's what I think definitely general equilibrium theory does in some sense. And then on the other hand, we have Keynesian macroeconomics, which is fantastic. I've absorbed it. I was a student of Mike, by the way, in a way, after graduating, took his class at Harvard when he was teaching that book before it was published. It has huge success for obvious reasons. And it's definitely general equilibrium in the sense that there are many markets, okay? But it's not general in the sense of general equilibrium. It's a series of examples that we work each time, but idiosyncratically hacking this or that. And we work with different objects depending on the application, an Euler equation here or something else. And so there's kind of this gap with the theory, and I would also say that creates a gap of intuition that I'm also going to try and expand on, okay? So that's kind of what's going on there. And it was hugely successful because it solved a problem nobody could study until it happened, and in years people figured that out. And people have been trying to do it from G, and well, that was this equilibrium literature that I'm going to talk about a little bit too. And so what we're going to try to do is fill this gap and really take the best of all these literatures. That's really kind of the point here. Here's a timeline just so you get a sense. People were working on macro, obviously, you think of Keynesian macroeconomics. From a G angle, you think of Patinkin, Klauer. But even after that, in the 70s, this equilibrium guys that were working on that. Okay? And from a more general perspective, this links to the topic of tatonement, because if you think of
a price adjustment theory in general equilibrium, it was all about the prices being out of equilibrium. And, you know, that kind of resonates with the Keynesian idea. Okay, so there was a lot of things coming together. And for us, actually, that's where we're coming to this. We're coming together from that angle. Okay. All right. So that's what we're going to do. We're going to create a framework. So it's a little different paper. I said that last year, so I guess I'm writing 2 papers in a row. But this is a little different paper. It's not like, okay, here's this one issue. Let's attack it with this model or look at this. I'm trying to go back and think about what are simpler principles so we can organize the models we have, which are great, and extend them. So basically, this is not replace anything, extend. Mm-hmm. So, but to do that, we developed this whole thing in this other paper, and I'm going to out and show it to you again in a different light and focus on the macro angle. And so our framework is going to look at, you know, quantities and welfare at points in time through the lens of an excess demand function. Mm-hmm. And then there'll be price setting that we have to think about in terms of that excess demand function as well. So what are some of the main results here, just to give you a sense, is I'm going to link inflation to excess demand. Okay. And that I want to do, okay? That's not what we like. I'll show that there. It feels really close to say how the gap is like excess demand, but it's not exactly the same. And as long as soon as you go beyond 1 or 2 goods, we know that it's not the same. Okay, so that's what I'm going to do. And I think that's going to be very simple and general, right? Okay. And in the form of a column type Phillips curve, which is called a pricing layer, I'm going to get a Phillips curve that looks a lot like your Keynesian upper gap one, but this is a fairly general model for any number of goods, and Z is an excess demand function. Okay, so this is a sense in which I'm bridging that gap. You just put down Mascolel, and you read all about the generality of how you can think of many things as excess demand. Okay, and now you know, they already tell you what an equilibrium is, but not anything about dynamics or of prices and so on. You come to this and you can see, you know, you're directly latching onto the same type of objects and intuitions. Okay. Okay, and it's more general, yet more intuitive. Okay. So that's kind of one of the selling points here. And what is appeal to authority? So here we're stuck between the great Fernando and the great Mike. And I hope you pay attention to my talk, but it's okay if you don't. But and I'm not even just to appeal to authority. It's like it's important that our macros sound not wacky, sound natural. And this is going to be very natural. It's going to say prices go up if there's excess demand. And that's what we teach all our undergraduates. And that's what a Phillips curve is. That's the point of this paper. Okay. So no by good academics that then later use it too, that, you know, that the Phillips curve is dead or something, or that it's some wacky Keynesian idea that doesn't make sense. Okay, no, it does make sense, but you know what I mean? Like it still feels like it's a little foreign from the Mascolel book. No, this is it's going to be, you know, this is going to give you that justification for saying all we're doing is what you get taught in micro. Actually, the Phillips curve is what you get taught in macro, in micro. All right, so I hope to convince you to take a look at this approach, and it's more general, simpler, and intuitive, and I think powerful, and it takes the best of 2 ratios. So it's you know, it's better, and I think it's also trying to raise up the reputation of this statistical literature, okay, for some of the things it did. So you'll see where that comes in, and so what's my plan? Just to organize the rest of the talk is I'm going to this approach that'll take most of my time, and then I'm going to do some applications and extensions. Okay. Okay, so I'm going to start building it up with something that's basically not doing anything. Let's just remove Mascolel real quick. Okay, 0 sub 0. The notation is we have general equilibrium. Can we kill that thing? There, I got it. So, you know, general equilibrium has the word general in it. So we got to be general. So we're going to have general primitives, any number of goods. Factors could also be goods. So goods or different types of labor could be good. Okay, different skills of labor. Any number of households with general preferences, any number of firms with general technologies, including if they buy stuff from each other and put output, which is very interesting. general preferences, but convex, so that we have the kind of assumptions we had for existence of equilibrium. And then purchases are X and sales are Y, or you could say demand is X and supply is Y. And we're going to look at the difference and call it, net demand, Z, okay? So Z is a vector of N goods. Remember, goods could also be different forms of labor and such. Okay, so that's the setup. Now, that's thinking. Next, I'm going to show you some math and some figures, color-coded in the following way. Okay, so some of you might have seen this in other talks I've given. All right, so, oh, wait a minute, this doesn't look like the right slide. Okay, here we go. So you maximize profits with the inner product between the price vector and the net demand vector of a firm F. They're maximizing that subject to a technology which is just a set of feasible things they can do. So this includes some of these are positive, that means they're selling them. Some of them are negative, that means they're buying labor and other inputs, okay? And then they care about the minus the inner product, that would be their profits, their revenue minus their cost. It works out that way with the signs. And if you maximize that, you get a demand function that I'm going to call Z double star for firm F. This is for one particular firm as a function of a price vector. Okay, that's standard Mescavel type, error de Brue. On the other hand, for households, we're going to have an H, they're indexed by H, and we have a utility over net demands. If they grow tomatoes in the backyard, they really get utility of eating tomatoes, but then we already embed that into this definition. You can define already the utility over net demands in purchase in the market. And they have some utility, and we're maximizing that problem. Where the left-hand side is, again, that's inner product, and that's how much they're spending on goods, but also because some of those are negatives, it's income they're earning. So a main example is, remember, some of the Z's for a household would be negative. That's their labor supply, okay? And then the right-hand side is boring. It's just some initial assets or ownerships of the firm. So then, again, we maximize, we get these net demands for the household. This is reviewing Mescavel real quick. Now you add them up, and you get the total net demand in the market with a double asterisk. And using double asterisk, you'll see why later. There'll be a single asterisk version of this, okay? It's more constrained. This one's like totally maximizing everything they want, and so double asterisk. And then an equilibrium is simply a price vector P and such prices that clears all the markets, so setting that Z function to 0, okay? So now we're going to do the first thing here, which is very simple. I'm going to add market power. And I'm going to do it in a way you're familiar with in all trade models, growth models, macro models, nothing new, except embedded in this general notation. I haven't seen someone who does it, or I would be happy to just say, look over there, okay? And we're going to do it this way. Each market, it's the usual thing. If we speak of white sliced bread, okay, then that's the good N that I'm talking about. And within that N, we're going to like there's a bunch of competitors, okay? We're going to do the extreme of thinking of a continuum of them that offer different varieties of white sliced bread, okay? And that's omega. And then each market like that is going to be distinguished by the people that set the price for that good. Well, that's just the producer of the sliced white bread of that variety in this case, and the guys who didn't set the prices. So there'll be a sort of price taking undifferentiated side. Why undifferentiated? Because like if you're buying bread, the guy who's selling it doesn't care if it's Fernando or Xavier. Okay, he doesn't care who he sells it to. Whereas when you go out and buy bread, you kind of care about these varieties. Okay, there might be not perfect substitutes. Okay, so they have the price setting side is also a differential side of the market, and that suggests a notation using U for undifferentiated and V for varieties. Okay, and this equation is an identity that's going to hold all the time because any bread that's sold is bought by somebody. Okay, so this is in aggregating across agents. I don't have J or F here. I add it up whenever we see something that doesn't have J or F. I add it up. Okay, so this is just saying markets are clearing, that's an identity. And the differentiated side is going to be handled by some agent J. It could be a firm or a household that sets the price of that good. Okay, we're going to assign goods to agents that way. And think about it like this typical case of used to monopolistic suppliers. In that case, the Z is some minus output that they're selling. But it could also be monopolistic demand. So it's like, I guess Harvard has a little bit of monopoly power in setting its wages because people are desperate to go to Harvard and get the Harvard name. Okay, so that's I always have to put a dig for Harvard here, but that's the monopsonistic. So this under one roof we're going to have monopolistic and monopsonistic setups. Okay, all right. And today, to make things simple, each agent is going to be assigned at most one market, but some agent might not be assigned to any market as price setters. Like you could be a retired guy that just buys everything and doesn't set a single price. Okay. And think of remember labels are good. So think like if I set the price of that good, it's kind of like my wage I'm setting. Think of it like a reservation wage in a rough way. Okay? Now, the undifferentiated side within a market, we're going to have to aggregate, and we're going to do CS, the simplest thing. So Dixit-Stiglitz, we have done other things, and it's similar, okay, for our purposes. For the construction I'm going to build, we'll see. You'll kind of sense that that's true. So here's the construction, and here's the stuff. For an agent with a firm that has control over the price of some market N, I'm just adding that blue term for the revenue. If it's the hiring of assistant professors, that could be a negative cost, but they're controlling the wage. That would be the PVN. And then I just expand what technology is. And then they're just subject to this demand function where they take is giving the total demand, let's say for a sliced white bread, and then can, if they charge a different price than their competitors, get more demand or less demand. Okay, the minus sign is just because of we're working with excess demands and so on. Everything's symmetric up for a household. Okay, think of a yeoman farmer or something. Now, if you solve this problem the standard way you would approach it, at least I've always approached it, is like you make a guess for the price vector. Let's say we're looking at flexible prices for the price vector and the quantities, and you look at these best responses, and then you look for a fixed point. That's like in 2 times n dimension, both in prices and quantities. You need both. That's often emphasized. You need quantities, not just prices. The first step I'm going to do is show you that we can look entirely at prices. Okay, that result is sort of new. So let me show you how it's done on a graph first, and it's very easy. So here's a okay, this is a bad set of slides actually. Okay, here's a marginal cost curve, and then I've augmented it by the markup. Okay, and then I already set it up. So in equilibrium, so this is a firm that's saying that has this marginal cost, augmented by a constant markup, which we know is relevant for a Dixit-Stiglitz facing demand curve. Here's the demand curve. Okay. I'm really upset. This is the wrong set of slides. Okay. The important thing here is the firm faces this demand curve here. It takes this number as given, but then it knows that if it sets a price for its own variety that's higher, it will have less demand. So this is like the amount of bread everyone else is selling. Okay, everyone is charging this price. They're selling this quantity. If you're a bread seller, you could charge a lower price and sell higher quantity, or you could charge a higher price and sell less. Okay, that's the green line. And the optimum here is set up so it's the intersection of the green and top red line. Okay, and why is it that that's the case? Well, that's just the condition for the optimality as I've re-expressed it. Okay, but notice that that looks like supply and demand now. Okay, so that's the basic observation. It's kind of trivial here in this case. It's a little less trivial in the later, but that's kind of trivial. And I've also set it up so that it actually coincides with what the competitors are charging. So it's kind of consistent with being a fixed point of under flexible prices. So the bottom line is, you first think about a supply curve where you don't impose a symmetry, but then in equilibrium, if everyone has flexible prices, prices do have to be equal to each other among competitors because everything's symmetric, and then we just get supply equals demand. So this shows that an equilibrium with price setting can be expressed as the same set of equations you look for in a Walrasian equilibrium. Okay, and this is the way to see it very intuitively. Okay, so I had the whole thing here. I don't know why I'm always getting the version without the. Okay, something's off. Okay, so what this does is, starting from here, I just justified that you can go to an as-if economy where you take the prices as given. Okay, this is not exactly true. There's a markup that I'm missing in this slide, but in the next slide, I'll show you how to do it more generally. Okay, but maybe that means we can just compute the excess demands and go back to the same equilibrium condition as before. Okay. Now, this is a cousin of things people say, that these economies with markups are similar, except for the outcome being as if you had taxes. But this is not saying that. This is saying when you're looking for an equilibrium, you can look at it from the perspective of a Walrasian equilibrium. Okay, that's the slight difference of the idea. Mhm. Okay. So now I want to do this more quickly. And to do that, the basic result here is if you have monotone pricing in the following sense, if you fix everything and you increase that quantity of white sliced bread that's demanded, if the price I want to set goes up with that quantity, okay, then we can always write these excess demand functions and do things like that, okay? That was true in my figure because I had that upward sloping supply curve from convexity of technology, okay? So here I showed that works also for a household, which is a little less obvious, okay? So you work through that, and the basic idea is the following. Let me try and do this. You have a utility function, these goods, and I've added, sneak something in. That's why I have a hat over this utility. For generality, I've included the possibility of an optional outside good, okay? That's what I is. I is, if you don't like it, imagine I is fixed at 0, okay? But I've expanded what I had before to have an outside optional outside good. We'll see why that's useful later. And I'm going to maximize that utility choices I had before. So I have the budget constraint I had before. I've just added the outside good on the left. So this is like money you don't spend. Think of it that way. Okay. And you're getting value not spending some of the money. And then other than that, it's the same problem I had. If I maximize of the goods in which I participate on the undifferentiated as a price taker, I maximize over 0 and I maximize the outside good only. So I'm not choosing here the prices yet for my sliced white bread, and I'm not choosing how much white sliced bread I want to sell. So then my utility depends on the price vector, all the vector, because I need to know the price of wheat, the price of renting a bakery, front store, etc. The whole price vector matters. But then I'm also conditioning on how much I'm selling and how much I'm charging for that, okay, up to now. That maximization here, okay, so I'm going to get rid of that constraint then, because since I'm conditioning on those things, I'm going to throw that constraint down. I'll use it in a minute. So I'm doing like a 2-stage optimization here. So in this inner optimization, I'm not choosing how much I'm selling the bread or its price. I'm just choosing the other stuff I'm buying. And that's what I'm calling Z star, one asterisk. And that depends on the price vector and the quantity of sliced bread I'm selling and how much I'm selling it for. And then under symmetry, which we'll get to back in a minute, if we want flexible prices, we would have to evaluate this at prices of white sliced bread equal to each other. Then you can just drop the other price because it's inside that price vector. Okay, so I'll get back to that function in a minute. But now let me look at the outer problem. This is like the price setting problem for a household, okay? And they're setting the price subject to the demand curve. Now I have the demand curve there. And that's going to give some optimal choice for the price and for the quantity that they sell. And that's going to depend on the whole price vector, obviously, which includes the price of the competitors, and also on the total demand, which is kind of how far out is that root line, okay? So that's the quantity of, the people are demanding. That's just a number for them, okay? But if this thing is monotone increasing, you can invert it. So I can solve, if this is increasing, instead of thinking about ZUN as something I take as given, for a given price I'm going to end up with, it must be that I know what the quantity is because I can invert. So that step tells me that I know what this quantity is, okay, as a function of the price that I charge. Now, it's not that I'm a price taker. This is like describing the low P of quantities and prices that I'm willing to have chosen. Obviously, whether I chose them or not will depend on where the green curve is. Okay, this is like telling me the schedule, that red schedule I showed you earlier. Okay, all right. So from this, I get the function with a single asterisk and the two functions, the two other functions. Okay, so let me show you on a figure real quick. This is what I had before. Okay, and you notice that if demand shifts up or down, I'm going to increase my price if demand shifts up. What I'm trying to rule out is this weird case. Okay, that that schedule would have been downward, and then my price might go down when demand goes up. Okay, there's always one intersection, don't worry about that. Okay, that's true by construction. But I'm ruling out this case, which is eminently reasonable, let's say for labor, that it bends backward. That's fine. Okay. So I need that monotonicity. Under that monotonicity, I always can use this excess demand approach. And what we show is that if markups are not too large, whatever they are large, if the ZV grid is still the way that makes it a normal grid, okay, so like leisure is a normal grid, then you have this monotone pricing condition. Okay. So that's the sense in which this is so trivial, but maybe discover you need some condition. Okay. But they're very weak assumptions that give you this. Okay. All right. So that's step one. And maybe I'm going too slow here. Now I'm going to add pricing frictions. Okay. I'm going to do that first in a static setting and then add the dynamics. Okay. So the static setting is going to look a lot like the disequilibrium type literature. Okay. Except there'll be a new result, which is this idea of what price pressure is. So I'll tell you about that. Okay. But there also be a result in that we're going to solve for the equilibrium form, which that literature struggled with. They couldn't. Okay, and I could explain why, but probably do that for questions later. Okay, so let me just jump into that. That was a summary ahead of time. So imagine all prices are set at, for white sliced bread, they're at some value, 1. Okay, and nobody can change their prices. They're fixed. Except me. I'm the only one. I'm measure 0. I'm the deviator. What price do I want to set? Okay. Well, we just kind of proved it. It's that red curve I defined and the green line intersected, which up to minus signs and how it works out is it's just solving this equation, which graphically was just saying, here's my supply curve, my demand curve, it's that point up there. Okay. So if everyone has their price here, but I'm the lucky one who could choose a price. In this case, I want to set a price higher than that. And I'm going to call that price pressure. This distance, because I'm raising the price relative to them. I'm the lucky one who can change prices. You can see why this is going to be obviously useful once we have something like Calvo. It's going to tell us the direction in which people are changing prices. But for now, it's just a hypothetical. Okay? And look how trivial this is. Micro, I like simple. Well, this is going to be positive if this distance is positive. And it's going to be the higher this distance for given curves. Okay, and from now on, I'm linearizing. So actually, that gives you a closed form expression. If you tell me this quantity, I can tell you that quantity. Okay, everything linearized around an initial equilibrium. Okay, so this is the first result, which is when everyone has their price stuck, we just need to know what that quantity is, the excess demand, and we'll know how much higher I want to set my price. And that's something I call price pressure. Now, this is new in the sense it seems trivial, but I haven't found a place where they do it. Okay, and I have, Jerry Green paper that's it starts off saying even the disequilibrium literature kind of talks about this, but doesn't have it. So, but we'll see how that fits in later with the framework. The next thing I want to do is solve for quantities given all those prices are fixed. Okay, so given all those prices are fixed, and now forget that there's a deviator for a second, it wouldn't matter. Okay, what is the quantity of sliced bread that's being demanded? Well, it has to satisfy this Z star we calculated. As follows. Everybody's optimizing, so it has to solve their Z star. The quantity of goods they buy on the price taking side has to equal Z star of U with the price vector P, taking as given these quantities. Okay, and finally, we also know that these quantities satisfy this identity. So plugging this in, this is just a fixed point condition for ZU. Okay, a Keynesian cross of sorts. Okay, so the ZU vector just solves a system of equations. Okay, as simple as that. Linearized, you can express it this way, but the important thing here, there's a step you're missing, but basically this is the fully optimal Z double star now. So what this is saying is, if the price is at the equilibrium, Z tilde is the excess demand now. Okay, the excess demand will be 0. Notice that satisfies this condition. But if the price is not at an equilibrium, so that this excess demand from the fully optimal perspective is non-zero, then these Z's will not be zero. And they have to solve this equation. This is kind of capturing that, like, if you went out to buy toilet paper but didn't find it, you might buy tissue paper. Okay, A is capturing the fact that since you didn't optimize over this, that has an impact on your demand. This A is just the Jacobian coming from here, and that's capturing that sort of effect that you'll get. The more relevant effect in a macro perspective, this is what Klauer and Patinkin talked about, is if firms get more demand, well, they have to hire more labor if their price is fixed. And likewise, for workers, if they get to sell more of their labor, they'll buy more goods. Okay. So this has already, I hope you notice, looks a lot like an input-output structure. For given P, fixed P, this is just a vector, and I have to solve this vector. Well, of course, input-output and network theory is just linear algebra. We do this, and we make assumptions so this exists. Okay. And then typically we make some further assumptions so that we're not scared that it's an unreasonable solution. In particular, the spectral radius of A, the matrix A being less than 1, that in the scalar case is like saying, your marginal propensity to consume is above 1. Okay, because then you can get rid of stuff. Okay. And this just captures that we want the total effect to be the direct effect plus the indirect effect plus the second round indirect effect and so on. Okay. But up to here, nothing complicated. But I just showed you how to solve for the quantities, okay? Given the prices, in a very general model, okay? If I have preferences, I have this A, I have this Z double star, and I can calculate then in closed form the equilibrium. So this is what's different from this equilibrium literature, that they were not able to do that. They got bogged down in many cases because they were, I could explain why. Here I'm linearizing and I'm taking advantage that there's a markup. So it's not really that you're rationed. You want to sell more bread at the given price. So I'm exploiting that. Whereas that literature departed from a place where you were at a kink, and then there were 2 to the n regimes that you had to consider. It was a headache. So they only ever worked with 2 or 3 goods, and it was pretty complicated already there. Okay, kudos to them. This is a different setup. I'm importing one of the things I think is a good thing of the New Keynesian model, that we have these markups, so we have some wiggle room to not have to worry about that. Okay, am I missing something? Sure, but I think 97% of the time this is the right thing. 3% of the time the toilet paper crisis or something, we want the other thing. All right.
So
Yeah.
this is like a bit of a local argument. If there was a big enough deviation.
Yes, exactly. But it doesn't have to be linearized. In the paper, we do everything nonlinear. Okay, so what have we achieved? This equation and this equation. Obviously, we want to put them together. This is the excess demand we need to know what price pressure is. It's not the excess demand where the Maurasian one. It's adjusted for spillovers. That's how we call this. A is the spillover matrix. It's what the equilibrium literature called the spillover matrix. Okay. And when you have input-output from firms and so on, an important component of that is the actual input-output matrix, but it's not always equivalent. It depends on who's setting prices. Okay. All right. So it's going a little fast, but those two things combined give you that. I'm going to skip this slide in the interest of time and jump directly to the dynamic setup and show you how these concepts just directly look. This is something you could teach in a first-year macro class. Very simple, I think, after people have done the Muscadel. And I'm going to show you that very simply you can get to a general Keynesian Phillips curve that has this excess demand that I just computed in closed form. I gave you the closed form for it, and I'm going to show you now where the excess demand is. Okay. So what I'm going to do is I'm doing what I just did, a dynamic setup, by repeating it, the same spot market each period. So I'm abstracting from capital here. This is an extension to be done. Okay. So that the only kind of state variable is the prices. Okay. Which will have a little bit of the cowboy rigidity, okay, to be able to not have a non-trivial solution where things just jump, okay? All right, so this is a New Keynesian model, but as you'll see, the setup is much more general, okay? And also the approach is different. I hope you'll see that. Okay, so let me show you what the math is, back to my slide that I had before, but I'm just gonna add that now it's not static, so I add up the present value, that's the early price. Similarly here, the discounted value utility, arrowable price there, where Q is just the discount, nominal discount, all right? And now, and of course, I have to add also the Calvo friction. Okay, so that's the model. Okay. Let me show you how you solve that model. So for now, I'm going to set this Q to be beta to the T. Think of that as like the natural steady state one. And then we can bring in the other cases. In that case, to do the math simply, we're just going to have this beta to the T there, beta to the T. And if I think of the Lagrangian of this households problem, it looks like this. Okay. And the key thing I want to like point out is that there looks like a static problem. So what I'm going to do is draw an analogy. Okay, you have this dynamic problem, but when you're choosing the goods of the undifferentiated goods, how much bread you want to buy as a consumer, that's just in here. That's a static problem now. So here, mu part is the Lagrange multiplier in the budget constraint. And I did a funny thing of pulling it out. That's just so I could say that the slope on this one is 1. That's just a nice normalization. Okay. And firms are also captured by this under the convention that their U is 0. Okay. So this in one fell swoop captures everything. Okay. So that means now let's strip everything. Let's look at that thing. And now here's the payoff from the static analysis. That looks just like the static analysis where that's my utility. And I do have a value of an outside good that's linear. Okay. That means I apply my static model. I get all those demand curves that I derived before. But I have to note one thing. This utility function, this is the thing that Fernando was alluding to, has a constant marginal utility. So it's a Frisch demand curve. It's not a Marshallian uncompensated demand curve. It's a kind of compensated demand curve. Okay. That's kind of a detail for what I'm going to do today. It's more important for what I did in the other paper. So I'm going to not bang on that too much. Okay. But anyway, I have these demand curves and I'm going to skip the math, fortunately, of the kind of the pricing part. So that was the quantity side of price takers. Now for the problem of price setters, I need to choose the quantities and prices. They're solving a Calvo problem that you can read Jordy's book or who. And except here it's expanded, and what we show in the paper is that expansion leads to using the things we had. So just like you're used to doing in the simple case, it's not even any harder. Boom, you get that the rate of inflation in good N in white sliced bread is related to excess demand, plus the inflation in excess in bread tomorrow. Okay, so actually more intuitive, I think, is the following. You can solve it forward and say that inflation in sliced bread is the present value, a weighted average of current and future excess demand in sliced bread. But let me emphasize, only in sliced bread, not in all other markets. It's not like some mathy, result that, of course, if I have enough information, I can map it back. No, this is the micro Gary Becker Econ 101 thing. The price rises in the market only caring about what excess demand is in that market. Okay, so this delivers, I think. All right, Phillips curve is nothing but what we get taught in micro. So that's the equation. Actually, this is more general. This is the proper excess demand, whether or not we had the conditions for deriving the demand the way I did before. So I'll talk a little bit about that towards the end. Let's say if you have financial frictions and things like that. Yeah.
Maybe there's no time, but can you make it more concrete? So I'm pricing bread, but I know the price of flour will increase a lot in 2 periods. Why isn't the future increase in the price of flour?
It is in there.
Sure.
It is. That's a good question. It's in my excess demand. Okay. Because I won't want to supply it in the future. Okay. Because the price is going to be high. So I have a.
Suppose the market's always clear. Maybe it's not time.
No, yeah.
Markets though, still the case that.
No, this is.
Flour should matter.
No, it's mattering through. It is mattering through that. Let's talk about it later. But that's a good way to test your intuitions and stuff. Okay, so so it's a different perspective. Of course, it doesn't replace. You can use both, but I think this is a different perspective. It is new, and I think actually your question puts your finger on it. Let me show you some applications and extensions in what time remaining. So first, I kept saying excess demand not equal to gap. I just want to convince you of that. What did I mean? Well, like if you read a macro book, I think the reason why the single good case feels good is it almost feels like excess demand. But it actually isn't. I'll show you a graph in a second, but I won't split hairs there. It's basically excess demand, the one good thing. So when you only have sticky prices, not sticky wages, for instance, you are doing basically something quite similar. But as soon as you have sticky wages, there are more goods or an input output, it's not the same. Right? And that's well known, and that's why a beautiful paper like Rubel's exists. It tells you, look, you need the output gap, but you also need all these other prices in there. Okay. All right. So think of that, what that paper does. And you might think, well, let me get away with a new idea. Let me define output gap in each market, which has never been done. Like what Rubel said is, let me define an aggregate output gap and then show you that I still need the other prices. Okay. But let me show you. This is the one good case. If you only have one good, this is what people call a gap. This is the quantity, and this is the steady state one. Okay. But that's the gap. The excess demand is this. They're different. Yeah, but they're kind of proportional to each other. But now imagine the price of wheat goes up. But today, that's not good in the future. Then my excess demand already shifts upward. So my excess demand would already be higher, but the output gap is no different. Yeah. Okay. So this is emphasizing already in a very simple case, output gap, even for this little market, not equal to excess demand. Yes, Jory.
It's an equivalent formulation, which is in terms of the markup gap.
Yeah.
Which would work sector by sector, you know?
No, Dory, I could rewrite everything the way it's always been written. That's the point. That we're doing something different. Yeah.
That's the advantage.
Well, can I talk about that at the end? I have a slide for you, but we probably need to sit down. You always ask this. If you're setting your ways, you might want to continue your ways. That's optimal for you, maybe. I'm trying to provide an alternative. I think some people might pick up and find it attractive. I certainly do, and I think I'm trying to get through some applications that show you that. But just notice how general it is also, Jordy. Like this is just so general, and it's so simple and intuitive, like your Micro 101 discussion. That's already an advantage, I think. Okay. Let me talk a little bit about monetary policy, which, a Taylor rule, for instance, would be that the interest rate is some weighted average of the inflation vector. So that would give me the CPI inflation with some weights omega. Okay. And then some loading P, Taylor rule principle is P bigger than 1, to react to the interest rate, and maybe some shock to the interest rate. Okay. Now, this might be confusing at first, but basically I've worked in Q instead of I in levels, but in Q basically, okay, here I'm linearizing in things, but the Q is basically the same as that, but in P. Okay, right? So you differentiate this, you'll get this. Okay. So why am I saying that? Because the following is true. Before I worked under the assumption that basically like you had a steady state Q, okay? And I'm going to skip a little here and say, now look at the relative prices that are in equilibrium that you're focusing on. We're doing everything local to that. The final price vector in the long run is going to be proportional to that. Okay? These relative prices are given. Okay? And that means that, okay, I'm doing some steps here, that you can use the apparatus I gave you before where you just have this Z function. And you stick in here the price relative to that long run price you're headed to. That's where the determinacy question is going to come in, okay? But notice this Q now, like here, is a function of the current price. Okay, and this concept doesn't matter at all for this. So the bottom line is, when you substitute both, you're back to the kind of framework I was talking about. You just have excess demand function that incorporates the responsive monetary policy now. Okay. And basically, at a very intuitive level, goods could be cheap because the actual price dropped, or because the interest rate, became very low. All right. So goods today can feel cheap in both ways, and this is capturing that. Okay. So it's just as before. Okay. So that's how you do monetary policy. Let me show you what you do with Taylor rules. So suppose at phi 0 you had stability, but you would have indeterminacy. Okay, that's kind of what we studied in the other paper. We focus on stability. So, but a typical idea is, but now once I have that, I just use the Taylor principle. Well, there are two threats to that idea. One is, initially you might not have stability. So that's why we focused on that in the other paper. Sometimes you don't have it. You need conditions for it. This is not known in the New Keynesian literature. Okay, so there's examples that I'll show you in a bit. But even if it's stable, we might ask, is it true? Do we have a theorem that we can find an omega and a phi that does the determinacy? No, there's no such theorem. I'm sorry. And we provide something. Yep. Okay. So the answer to both questions is no in general. but we actually also provide some positive results, okay? So let me skip that in the interest of time. I'm mismanaging here. Here's an example where with phi zero, you have like a cycle, okay? And so you can get a situation where the Taylor principle is not going to lead to anything sensible. But we have a positive result that some monetary policy more sophisticated does. And by more sophisticated, it just means you might need negative weights. Okay? It's kind of weird, but and then we also explored some conditions so that you don't need the negative weights. Okay, so that it doesn't look so weird. Let me skip this because I want to at least scream out some results. Okay. Zero lower bound. How would you do zero lower bound with this? Well, zero lower bound is just a monetary policy that depends on time. Once you know when it binds. So let's say for the period here, Q is flat, fixed nominal rate. After that, I'm going to apply the Taylor rule. Okay. Then you just solve backwards the system I gave you with the excess demand function. It's a piece of cake. Okay, so this is really with price and wage rigidity, say. Okay, so you are really solving a general economy in this way backwards. Let me show you this and end with this because I think I'm going to have to skip the rest. So shocks to excess demand. I didn't put shocks to uncertainty before, but let me throw it in. This could be preferences or technology, sectoral things, or government spending. Government spending is nice. It would just be additive. It's like another agent. And then you just have to solve this equation. You just get the static multiplier here. Okay. And then you just work with that function Z that has a shock G in it. Okay. Okay. So that's more general, of course, but let me just mention this. But if you do aggregation, I mentioned already Rubo's paper because I think it's a fantastic paper. It works and shows you need this single scalar output gap and all the other prices. Or you can drop one of them, okay? Because only relative prices matter. And then the whole paper is about that struggle. But what we show here is, look, aggregation is immediate. If you have this, if you teach it like this, just add it up with it with your preferred CPI, and you will get an aggregate Phillips curve for that definition of what excess demand is. It's a weighted average of the excess demands. Okay. All right. So I'm going to skip these extensions, but we can handle non-Ricardian. It's a simple mix. It just changes your excess demand. It's not a constant margin utility anymore. You could do Hank if you like it. I know people here like it. And let me conclude. So we had this history. I hope I'm saying that, we're trying to merge good things that everyone had here. That's what the outcome of this is. Hopefully that helps close that gap where we teach with, excess demand functions and we jump to a Phillips curve and it's not something funny. It's basically a continuation of that involves the same objects and has the same intuition that your micro people talk about. Let me end with this for Jordi. From my advisor, appealing to authority in a different way, and appealing to Richard Feynman here, who explained the value of having an alternative perspective. Thanks.
All right, so I can complain on it. So, like.